So let me summarize what we saw in the past days. We are studying the quantumizing model. That is a one-half spin system. We have seen that this model has two phases that are separated by a critical point GC that yesterday, I believe, you have located in perturbation theory being 1. Right? So yesterday you did some perturbation theory, right? And I believe that you have computed the excitation spectrum. And so that the gap above the ground state goes like, there are some constants, and goes like 1 minus G, right? So you see for G equal 1, the gap becomes 0. And in this moment, this is our definition of a critical point. So the critical point is 1, as seen in perturbation theory. And for GC smaller than 1, we have the ferromagnetic phase that is characterized by the presence of a local order parameter, M, magnetization, that is different from 0. In fact, it's some function n0 of G, and non-vanishing connected correlation functions we've explained exactly in what state. And degeneracy and spontaneous symmetry breaking. So the fact that there is spontaneous symmetry breaking is equivalent to saying that there is a spontaneous magnetization. Because if we didn't spontaneously break the symmetry, if we were in the symmetric state, M would be 0. So you see, if this is true for the symmetry broken state, it's exactly because we break the symmetry that this thing is different from 0. For G C greater than 1, we have the paramagnet, where magnetization is 0, and connected correlation functions decay exponentially, which I've just claimed, I didn't show. So also this can be seen in perturbation theory. So now that you know how to do perturbation theory about this, you can also compute this. If you want to see the details of this, and I suggest you do it as a homework, it's on the SUChdef book, chapter 5, I believe. It's very well explained how to compute correlation functions from perturbation theory, and you will see this. But we will see in general that in this situation, when, okay, so this is a paramagnet, there is no degeneracy, ground state is unique. In one of the next lectures, we will see that this is a very general statement. If you have a unique ground state and a gap above the ground state, so away from the critical point, the system is gapped. But in the paramagnetic phase, it is also unique, the ground state. Then connected correlation functions are bound to decay exponentially. So this is a very important fact. So there cannot be long-range order. However, when you have symmetry breaking, you can have long-range order. You actually do have long-range order because you have the symmetric states in which we have seen that there is a long-range order. And a standing question is, can we have at the same time this type of behavior and degeneracy? Right? Because here we do not have this behavior exactly because of degeneracy. But are all degeneracies the same? Are all like symmetry breaking, or there are different types of degeneracy? So I'll repeat this question many times because we will see that in the future it will play a role. Okay. And yesterday we also pointed out that the symmetry breaking states, that let me call them psi 01 and psi 02, are also the most classical ones. In the sense that this quantity, the mutual information that is defined as SA plus SB minus SAB, where A and B are two subsets of spins, this quantity for macroscopic regions, so let me use this notation. This means that the dimension of HA, or actually the number of spins in A and the number of spins in B is much greater than 1, so number of spins, and that the distance, the graph distance between A and B also is much larger than 1, so that this thing in this limit goes to 0. In this sense, they're more classical. Whereas when you have the coherent superposition in psi, whereas infinity computed in psi 0 plus, the symmetric state that has a long-range order, this one is different from 0. I claimed that. Okay? This is something that we will prove in the following, but we need more tools to do that. But one thing that I show you today is the part that explains why we call it spontaneous. So I said many times that these are the only stable states. So we need to understand what this means. Okay? So in order to show you this, I will do the argument in the limit of g equals 0, because for g different from 0 is essentially the same argument, but at g equals 0 is much simpler. So for the sake of simplicity, we will consider g equals 0. And to understand the quantum case, we first need to understand the classical spontaneous symmetry breaking. Okay? So imagine that, in fact, for g equals 0, the Hamiltonian, which is just this part, is the same than the classical Hamiltonian. So you remember we said, I think the first day, that if all these operators commute, all the eigenstates are, if there is no degeneracy, are just the spin configurations that are classical states. And the only difference between the quantum and the classical state is that if there is degeneracy, in the quantum case, in principle, we can also take superpositions, whereas in the classical case, not. Okay. So in the classical, so let me first, in the classical case, our ground states are in fact all spins down, all spins up. So let me write it like this. And all spins down. I'm writing them as a cat, but they're spin configurations. I just mean all the spins are up, all the spins are down. And because we are classical, there are no other states. There are no superpositions. Okay? And we want to understand why the system spontaneously chooses one of these two states instead of being in some classical mixture of these two states. Right? So when we compute the magnetization, so, to compute some expectation value, you should, so it is this. This is the observable. And so let me compute the magnetization per spin. This will depend on your spin configuration, right? And you have a probability for this spin configuration. And then you sum over all the probabilities, so you have the expectation value. And this probability is the Boltzmann weight, right? It's e to the minus beta, the energy of the spin configuration, over the partition function. Now, if you take this average over all the possible spin configurations, so you have as many, for every spin configurations that has x spins up, you have the same spin configuration where everything is flipped, the symmetric one. And therefore, this quantity assumes the two opposite values, and the total sum must be 0. So if we take the average over all the possible spin configurations, no matter what we do, the average magnetization should be 0. So how come already classically we have a spontaneous symmetry breaking and the spontaneous magnetization that is left? And I said many times that we do this trick that we invent some initial condition, like to the Hamiltonian, instead of being just this piece, we add a magnetic field that favors one of the two directions. So we explicitly break the symmetry first. Okay? Then we do all our computation. So we find a non-vanishing magnetization. We compute it in the thermodynamic limit, and this is important. But, okay, the fact that this magnetization is now positive, say, is not surprising because we have explicitly broken the symmetry by adding a field. However, at this point, we take the limit of this field going to 0. And we still find a residual magnetization. So this is the usual argument that you find in textbooks. And I have never been completely satisfied with this argument, although it is correct. But it's strange because, yeah, in the end, we send to 0 the breaking part. But at some point, the breaking part was there, was involved. Yeah, I feel a bit awkward to say that this is so spontaneous, right? Because I cannot obtain this result if I don't break the symmetry first. So there is a better argument that is dynamical. Okay? It is telling us, depending on the initial conditions, we might be in the situation that not all the configurations are accessible. See, when I take averages in this way, so I'm repeating things on usual statistical mechanics, we are assuming that all these configurations are available, and their probability of being there just depends on their energy. But so we are assuming ergodicity, means that if this is the space of all our configurations, okay, so every point here is one set of spin values, they are all available. This means that if we have some initial condition, very quickly, the system explores all of them. And if there is no energy constraint with equal probability, if there is an energy constraint with this probability. So if we are ergodic, then we can take the averages like this. But ergodicity could be broken. Imagine that there is a wall for some reason that we will see. And then if you start here, you are confined to this part of the phase space. If you start here, you are confined to this part of the phase space. Now, this is exactly what is happening. If these two regions, this is one with positive magnetization. So you are in some configuration with positive magnetization, the instant t equals 0. You will be confined to only the configurations with positive magnetization. You can only average it there, and vice versa. This doesn't happen always. It happens with some conditions that we will see. This condition is a temperature. So below a certain critical temperature, you will be stuck here. Above or here, depending on the initial conditions. Above the critical temperature, you can explore everything, and the average is 0. So this initial condition plays the role of that external field that we put when we show spontaneous symmetry breaking using the method of sources that we first put there, and then we take to 0. What really happens is a dynamical behavior. Now, we will see that ergodicity breaking, in what really matters is the fact that the system is large. So the thermodynamic limit is important. So let's see all this. How does it happen? So we are talking about stability, okay? So imagine that I start from a spin configuration that has positive magnetization, and let's take this one, the extreme one. All the spins are up, okay? So now now this is not the phase space. This is our spin system. So all the spins are up. And now we want to perturb our system because we assume that there is some bath at some temperature T. And this bath can couple to our spins and flip them. Okay? It's noise. And I want to show that this configuration under certain conditions is stable. So I cannot, I don't have a probability of going to the other configurations where all the spins are down. So that in the end, I only can average over configurations in which the total magnetization is positive. Okay, so how do we go about that? So what we say is this. So virtually, imagine that our environment flips some spins. Okay? So we have a little domain of spins that are flipped. And we want to see, if we do this, how our free energy changes. So what is the change in free energy? Why we want to do this? Because we know from thermodynamics that if a spontaneous processes always lower the free energy. So if we have a big increase in free energy, this process will be forbidden. In fact, being a stochastic process, the probability of some process, the probability of going from the configuration 1 to the configuration 2 goes like e to the minus delta f, where this is the difference in free energy between the configuration 2 and configuration 1. So you see that if there is a big increase in free energy, then the probability of this happening is very small. Or in other words, the lifetime of configuration 1 is exponentially large in delta f, right? Because the probability, this is the probability per unit of time. Very well. Okay, so what is delta f? Is delta E minus T delta S. So we need to understand how our energy changes when we create a domain and how our entropy changes when we create a domain. So you see this domain has some boundary. So let me call this domain A. At the boundary of this domain is delta partial A, partial boundary of A, and when I put this symbol, means this is how big is the domain. Okay. In this case that we're in TD, this is a perimeter, but can be anything. So the argument will carry in any dimension. Okay, so let's first compute delta E. Okay, so you see that when we have all spins up, our energy is minus J. So E of the configuration, the first configuration, is minus J times the number of spins. But when we flip some of them, for every pair of spins that have different direction, then we get an energy plus J. Do you see that? So this means that the gap between the two configurations, let me see where I can write it. Let me write it here. So the gap between the two configurations is equal to J2 times the number of spins, the number of pairs that are broken. Let me say, use this word. And how many pairs are broken? It's a number that goes like this. Okay. Now let's compute the entropy. Well, so, the entropy is K log the number of configurations that give me the same macro state. For us, my macro state is a region of flipped spins with this boundary. So in how many ways I can create, you see, these are all ways of creating different shapes that have the same boundary. And how many ways there are? What do you think? So imagine that we are for the sake of simplicity, imagine that we are on a two-dimensional lattice. So my spins, we are on some regular lattice, okay? If the lattice is not regular, this number is a complex, very difficult number to compute. But imagine that we are on some lattice that has some order, and this is our region A. And I'm asking you, in how many ways I can change this region, keeping the boundary more or less the same? Well, the mathematically super precise answer to this is a complicated problem, but this number goes more or less like the degree of my nodes, so how many spins come out from my node, because you see, this means that I can change locally in a few ways that depend on how many spins I have that come out. So I can do this, let's say, in mu-independent ways. And I can do it in mu-independent ways for every piece of the boundary. So the number of configurations should go like mu to the delta E. And remember also that the initial entropy is 0, because we have only one way of putting all the spins up.
What's mu?
Mu is the degree, is a number that has to do with the degree of the node. So how many spins come out from the node? Because it's telling us in how many ways we can change this boundary.
But if you deform the boundary the way the number of, or the boundary of A changes, like
yeah, but it changes very little. It's similar boundary. If delta E, if this is a large number, a local move doesn't change the boundary very much. And remember that we are saying that the length of the boundary is basically the number of pairs that we break. Number of pairs that we break is mu. Mu is the number of pairs that we break.
So the number of configurations is mu in power.
Yeah. And we are computing delta S. The initial entropy is 0. So it is this number minus 0, delta S. Why the initial entropy is 0? Because the first configuration is all spins up. There is one way of doing that. So the entropy is 0. Log of 1 is 0. So this is a number. So k log of this is a number that is some constant times times delta E when I take the log. This constant contains k, is k times a number that depends on mu. Okay, some constant that depends on the lattice. So if we put things together, you see that delta F is equal to the boundary times 2J minus Ct. Right? We have the temperature here. So you see that this number can be smaller than 0 and greater than 0, depending whether T is smaller or larger than 2J over C. Also remember that in order to go to a configuration where spins are negative, where the magnetization is negative, this region must be very big. Means that dA must be very, very large. Must be a something that scales in the thermodynamic limit. So depending on this number is either plus infinite or minus infinite. Or actually is this number, so instead of taking the thermodynamic limit, let's take the asymptotic. It's something like the square root. It's like n is the number of spin, to 1 over d. This is the dimension of the space. Okay? So you see that if we add in more than one dimension, and we are below the critical temperature, then this term wins. The free energy is negative, and we cannot tunnel to configurations that have negative magnetization. Do you see that? Because this probability scales like, so this will go like, so let me call this number small delta f. So this is something like, let me go in two dimensions. Okay. So if we are below the critical temperature, this number is exponentially small. If we are above the critical temperature, this number is exponentially large. So there is a critical temperature that is this number. below which ergodicity is broken. Notice that in 1D, the boundary, so if our system is a spin chain, and this is our region A, the boundary, so how large is the boundary, so how many pairs we break, is a number, it's 2. It's a number that does not depend on the region A. So only in 1D, this will not scale. So this means that this probability is just a number of order 1, which means that there is a finite probability of tunneling. So in 1D, there cannot be phase transitions, okay, because of this. But in 2D, and more for the IC model, the free energy barrier between the two configurations scales with n. And so ergodicity is broken, and you are trapped. And you are either in states with configurations with positive magnetization or not. Okay? So this is the classical argument. And this argument carries over exactly the same, because it's the same Hamiltonian, if we consider the symmetry broken states. So we know that those are stable. Okay? Those are stable, also quantum mechanically. But now we have to say something more, because now we are in the quantum mechanical case. We also have the coherent superposition of those, and we must show that those are not stable. So we have to show that when I take superpositions of this type, so they are not the maximum symmetry breaking, that these are not stable. So let me, for the sake of simplicity, and there is no loss of generality, consider this state and its counterpart, it's the orthogonal state, that is this one. Okay? So I want to show that no matter what, no matter in what dimensions, what is the temperature, the tunneling between these two states has a probability that is finite, that does not scale with the n. So taking the thermodynamic limit will not make these states stable. Before I go ahead, notice that here we are talking about, you see, a lifetime that scales with n. This is what we mean by metastable. This means that if we first take the infinite t limit, because our system is finite, so it's n large, but it's finite, then eventually we recover, we do explode all phase space if we really wait infinite time, and the total magnetization is 0. However, the system is effectively trapped for a lifetime that goes like e to the n, which is more than the age of the universe for n that is 10 to the 23. Okay, so that's when we say metastable instead of stable, this is what we mean. So you see the importance of scaling with n as opposed to a number, doesn't matter if it's large or small, but it is order 1 that does not scale with n. Okay, let's see that these ones are not stable. So why these are not stable? The point is that you see the difference between all spins up and all spins down. What is the operation that sends one in the other? It's our symmetry operator. The very fact that this will go by flipping all the spins in this has a very profound implication. This is a global operator. The fact that two operators, the two states are globally different in this sense, in the sense that I have had to flip them have to operate with a global operator, has the implication that they can be distinguished by a local operator. In fact, I can distinguish the state at 0 from the state 1 by just looking at the magnetization of one spin. So that's why when we have spontaneous symmetry breaking, the order parameter is local. Okay? So the very fact that there are local operators that distinguish these two states, this means that they would. What does it mean? That in the basis 0, 1, this operator has matrix elements like this. Right? So it's not 0. It's not a vanishing operator. I have matrix elements. What happens if I change basis? So if I do a superposition of 0 and 1, I will get off-diagonal elements. Therefore, off-diagonal elements are tunneling amplitudes. So the existence of a local order parameter in one basis implies a tunneling amplitude in another basis. In other words, which you could check immediately, this operator applied on the state plus makes me tunnel to the other state. I could have said that from the beginning. The way I'm saying like this, it's because in this way it generalizes to any superposition. So you see, the very fact that we have symmetry breaking means that the operator that makes me tunnel from this to this is local now. So you see, the whole argument that something has to scale like the boundary of A breaks down. Because in order to tunnel from the state plus to the state minus, I just need to operate once locally on one spin. I just need to touch, to just graze ever so lightly one spin of all those spins to immediately tunnel to the other state. So if this is a stochastic process, because these perturbations are given by the environment, the fixed point of this process is that I am in a mixture of either all states being like this, or all either the system being in this state, or either the system being in this state, which is a non-coherent state. The fixed point is in the basis plus minus, I will have half of probability in being in this state, half of probability in being in this state. So I'm not breaking ergodicity. I can explore both these configurations and those configurations. So you see, the very fact, the fact that we have symmetry breaking at the quantum level implies two things. Implies that there is a basis, which is this tensor product, in which states are stable, and all the others that are superposition of this, because this is a basis, are unstable states. The way Zurek says it is that the pointer states, so the stable states, are those states that are tensor products in the degrees of freedom that are those that the environment couples to. So because the environment can address the spins one by one, this means that the only stable states must be those states that are a tensor product of spins or classical states. So that's why you don't have cuts when you have symmetry breaking. And this is also the reason why we have hard drives. Because, as we said, this state can be stable, this state is stable, this state is stable. So if I have some magnetic system with a certain number of atoms, and all spins up is the bit 0, and this is the bit 1, then it stays like this for a time, unless the temperature is too high, right? Because we have a critical temperature. So if you are below certain critical temperature, this domain will not change without error correction, spontaneously. That's why you can switch off your computer. You're doing nothing to it, and when you switch it on the next day, the information is still there. Because you have broken ergodicity. However, if you put it in the oven, you will lose all the memory because you go above the critical temperature before you melt down the actual physical hard drive. I believe at 50 degrees it fails, or something like that. That's why you need to cool them. So the question is it possible to have superpositions that are stable, macroscopic superpositions that are stable? Is it possible to have Schrödinger cuts? What we answer today is that it's not possible by symmetry breaking. If these two states exist because symmetry breaking, then this operator must be local, because we have a local order parameter. But the more general question is this impossible in general? Is it a law of nature that we cannot have Schrödinger cuts? It's just something very rare. So the answer that we have today is that as long as the only type of order that we have in a condensed matter system is determined by symmetry, then it's impossible to have long-lived quantum states. The only long-lived states can be classical. Okay? So you see that we have a very interesting connection between the type of order that we have in a system and the statistical mechanics, and also the information theoretic property of these states. Okay. So this is so let me also comment that we do have hope because we discovered that there are other types of order. However, this is still an open question, whether, the fact that we have other types of order means that we have a door that is open, but we don't know yet. In fact, the only system that as a model works is in 4 spatial dimensions. And yeah, so is it possible to have it in, in less than 4 so that we can do it in the lab? Can we build a quantum hard drive? We don't know. So this is, and I believe this is one of these very hard problems that can be solved. No, it's not like saying, oh, I want to solve Ising model in 3D, which means that, if you choose that as your PhD topic, you are ruining your career. But this is a hard problem that somebody much smarter than those that are around here, than me and other people, but you guys maybe can solve. All right. So now let's continue. So now we know why in a book like Sachev or all other books, when they say, OK, we have symmetry breaking, then we have 2 states, all spins up and all spins down, and not the superpositions. It's because of this. So yesterday, you guys located, by computing the spectrum, you located the critical point at 1. You did it in perturbation theory. So there are other two ways of doing that. So one is to solve the system brute force. The quantumizing model is a solvable model. It's exactly solvable. You can get the exact spectrum and eigenstates by a technique that I will show you. But before doing that, I want to show you a very powerful and elegant argument to find the critical point that is called self-duality. Okay, so what is self-duality? First of all, so what we do is that we define a transformation of our degrees of freedom that we call dual. And then we will see that under this transformation, our model goes into itself. Goes in the same model with some different coupling constants. So if under a dual transformation, the model goes into itself, we say it's self-dual. What is the dual transformation? It's a transformation that, first of all, sends the original lattice. So let me do it for the spin chain, for d equal 1. Oh, by the way, when I say that the Ising model is exactly solvable, I mean in 1D. So the dual transformation sends the lattice to the dual lattice. What is the dual lattice of a lattice? Did you study chemistry? It's the transformation that sends the bonds of the old lattice in the sides of the new lattice. So if I'm labeling the sides with the label I, and this will be I plus 1, and I'm labeling these sides with M, and then plus 1, you see that M depends on I, because in terms of the old lattice, this is an edge, right? Because in the new lattice, it's a side, but in the old lattice, it's an edge, and it's the edge I plus 1. Okay, so far, so good. Now we want to transform our variables and find new variables. So our Hamiltonian is written in terms of these sigma variables that are the Pauli operators. We want to define new operators called mu. So mu1 of M and mu3 of M. Let me just look, because I always mix them, and I want to be consistent with the notes. So, okay, mu1 is the Ising coupling. Okay. So I remember that M remembers who is I, right? So this will be for us, it will be defined in terms of the old variables in this way. Okay, whereas this guy is the product of over all the spins that are on the left of M. So let me write like this, of sigma x. So notice that this is a string operator. It's a long string. And it's non-local. So this is a non-local transformation. Okay, so these are some operators. And I'm wondering, after I do these transformations, these spin operators are, these operators are spin operators? Are they things like the first Pauli matrix and the third Pauli matrix? How do we know that? How do we know that? Why the Pauli matrices are the Pauli matrices? It's not because we write them like 1 minus 1 and 0, 1, 1, 0. It's not because of that. That's a representation in a basis. What matters is their algebra, right? So what is the Pauli algebra? Pauli algebra is the fact that these operators, first of all, square to the identity, which means that they have two eigenvalues plus 1 and minus 1. And second, that if they are at the same site, they anti-commute. This is the Pauli algebra. Now you see that they obviously square to the identity because they're just products of sigma matrices. So the square is the product of the squares. Each of them is 1, so they square to the identity. This one, you can also see it because what is mu3? Mu3 is this strength of axes up to m. And what is mu1? Mu1 is this bond made of sigma z on the spin that is on the left of m and the other one. So you see they overlap on one spin only. So here they commute because, you know, here this operator is the identity. They only overlap here, so their commutation relation is the commutation relation between x and z, which is the anti-commute. Okay. Oh, so these are spin operators. So if I rewrite my Hamiltonian in terms of the mu variables, I know that it's a spin 1/2 Hamiltonian. So let's just do that. So my Hamiltonian after the duality transformation is minus Gj. Okay. The sum over, so what is sigma xi? Well, we don't know, but look at this. Right? Because the two strings overlap up to m, and then they square the identity, and then I have one left x, that is this one. So the term sigma xi can be written in this way. And the other term is just the sum over mu1. And this is equal to minus G that G that multiplies minus J sum of mu3 minus 1 over G sum mu1. But these are spins operator. And this is exactly my same Hamiltonian than before on a different lattice. It's the same Hamiltonian. The only thing that, J is here. So this is equal to G, my initial Hamiltonian, where the coupling constant now, instead of being G, is 1 over G. So you see, it's self-dual. What is the consequence of this is that the spectrum in the mu variables is equal to G the spectrum for a value G of our model must also be equal to the spectrum of this Hamiltonian. So it's equal to G, the spectrum for 1 over G. If you compute the gap, it's the same thing. So if you now impose that the gap must be 0, and you assume that this can happen for only one value of G, so you have to assume it, And we already know that this does not happen for g equals 0 because we know that g equals 0 is not the critical point. So this is 0 if and only if, assuming that this value is unique, g is equal 1 over g, which means that g is equal 1. So you see, without solving the model, without doing any calculation, just because it's self-dual, I know where is the critical point. So this is a very powerful method because sometimes we know or we can argue with some assumptions that this is the critical model of other systems that we don't know how to solve, or that perturbation theory, is more complicated. Okay, so tomorrow we'll see the exact solution of the quantumizing model, and we will start developing these tools about locality that allows us to show what is the behavior of correlation functions and many other things, and introduce new kinds of order. Okay, that's all for today.